That was a joke. When did you post it? Not really. I posted the homework early Tuesday morning, around 3 o'clock, 4 o'clock. So it was posted basically Monday night, except for you extreme night owls. Any questions on the homework? So you actually looked at it?
I downloaded it.
How many people actually downloaded the homework? Oh, you did? Well, that's impressive. All righty then. Any questions on the material so far? We are now in the mathematics of the course. We're not going to go too deeply into this, but what I'd like to try to do as much as I'm able to before it gets too hit in chapter 7, because we're not going to go through all of chapter 7. Oh, no. I told you, that's a modern control course. But we're going to try to plot ahead a little bit more. And let's begin with trying to understand a little bit these diagrams the authors are throwing up. So let me write this at the board so I don't have to scroll back and forth. We've got a third order differential equation, y triple dot plus 6y dot plus 11y dot plus 6y equals u. 6u. Lots of 6's in there. Alrighty. Okay? So the way that the authors, we do it in this way is we first get 7.8, which is y triple dot is equal to negative 6y double dot minus 11y dot minus 6y plus 6u. And now we're going to draw a block diagram for that. We're going to say that this is y triple dot. Okay? Without looking at the picture now, we're going to say that's y triple dot. Now I want to draw a block diagram of it. How do I go? Y triple dot is this combination. So one of the elements in here is y double dot. How do I go from here with a block to get y double dot? One over s, an integrator, right? So this is going to give me y double dot. But I also need y dot. How am I going to go from y double dot to y dot in a block diagram? No. Somebody in the back who didn't hear the answer in the front but can just see it. Come on, you people in the back row. No, the very back row. Yeah, the guy thinking like the thinker. Or look at it. See people in the back row. I'm waiting for you. How many are you in the back row? 1, 2, 3, 4, 5, 6. There's 6 of you in the back row. Choose a candidate. Oh, there's actually 7 of you. I can see that guy way in the corner about it. Yeah, you're getting. There he is. He's high. How you doing? So you guys choose a candidate. Come on. Get amongst yourself, and one of you just speak up. Shout it out. We'll wait. And we'll wait. No. Back row. Yes. Thank you. Took the bullet. And now, all right, I'm not going to insult you anymore. Right? Okay? But this is y triple dot. So y triple dot equals a combination, a linear combination of things. And one of those things is 6 times u. Not u. There. That's one of them. This is a summing, right? What else? Now, how do we do the rest of the block diagram? What is the other term that you need to get to figure out what y triple dot is? It's minus 6 times y double dot, right? Here's y double dot. Correct? And what's the next term? And the next term? There it is. There's the input. There's the output. Okay. And all of the feedback elements. Let's go to the transfer function here. Everybody see this? Let's go to the transfer function. What's the transfer function for this system? You should all be able to do this in your heads. Somebody in the front row. Okay, so what you see that's being fed back here in the feedback is this number, that number, and that number. Right? Okay? And the 6 comes out in the front. So I told you, we're not going to go into heavy block diagram manipulation, but this should be, you should feel comfortable with this once you've seen it. If you haven't seen it, it's like, where did that come from? But now that we've done it, you should feel comfortable with it. That's what the authors get right here. Okay? But now what they do is they do the following, and I need red to do this. Okay? Y triple dot, we're going to call x1 is y double dot. Right? Then x1 dot is y triple dot. Right? And what comes into here, so this is x1 dot, which equals x2 dot. This is almost like a Rube Goldberg contraction based on what we've been doing so far, because it's looking really complicated, I think. Okay? And then this is going to be x2, which is x3 dot, and then, of course, the integral of x3 dot is x3. All right? Okay? So now what we can do is we can actually come up, that's what the authors give right here. This is x1, x2, x3, and x1 dot. That's exactly that lower equation right there. Okay? Or the picture in figure 715. Okay. And the authors go through, the basics, that picture on the top, which I guess that's okay, because that's how you're getting your states. You're integrating one state to get the next state, right? Okay. And so this is the picture, and this is the state space model that you end up getting. Okay. Let's see how we got that state space model from this picture. Because once you let's just do the picture. What is x1 dot? What's x1 dot? Well, that's y triple dot. So what is that? And what's x2 dot? So right up there in red. What's x2 dot? x1. And x3 dot? And now we just write this in matrix form. Right? So to write it in matrix form, just write x1 dot, 2 dot, x3 dot equals a big blob times 1, x2, x3 plus another big blob. Okay? Now what's the first row? This is just transforming equations into a matrix form. So x1 dot, this is x1. It's -6, -11, -6, right? That gives you the sum of those three because it's row times column. And then plus what? 6u. And what's x2 dot?
1, 0.
x3 dot.
0.
And of course, this is all 0, isn't it? Because in those lower rows, that's not there. So this is x dot equals ax plus bu. All right, and now to get the output, which is the output of the system here, that is defined here is the output. Remember, the transfer function, you start at the very beginning, you end at the very end. So the output is just y, which is what? x3. So if y is x3, then how do I write that as a function of this? Because this is a three-dimensional x. What do I need here? Remember your row column? This is just x3. That's the output. That's in that block, right? So this has to be 0, 0, 1. And then you can say du, where this is 0, because there's nothing there. So that's one state space representation of this, and it's given right here, at the top here, right? Okay? So you can verify this thing by doing numerator, denominator, in brackets is state space to transfer function, A, B, C, D, and it will give you that. Well, we started with that, didn't we? Basically, we started with that, didn't we? We didn't start with that. We started with the differential equation. But if I give you this differential equation, that thing you should say in 5 seconds is this. A little bit. You should all feel that comfortable to pick out a diffie q or a transfer function in y and u based on the diffie q. So we basically started with this, went to the state space, got an A, B, C, D matrix set, and then verified that that A, B, C, D matrix set actually gives us this transfer function. Because if this would have been something different than that, you would have said what? I typed in one of my matrices wrong. So it's a really nice, simple check. If you're starting with a transfer function, you go to a state space, do that thing, and get it back. All right? Now, it says following, if the transfer function were in desired factor form, it could be obtained blah, 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 blah. Sorry, I'm not going to get into the factored form. You can go and factor it if you want. I'm not going to go there. That's really getting more into polynomials and partial fraction expansions, and I just think it's second order effects. Let's understand the big picture first, and then you can go to other forms if you want to go to those forms. If you use this out on the job or in a graduate level course and then talk about these other forms, that's where you'll learn that there's a variety, the modal form, there's all types of forms. This form in particular is called the control canonical form. The controller canonical form the main thing about the controller canonical form is this. There are permutations of that form in terms of B and C, but the main thing is this. You have the first row, which is the minus the coefficients of the lower derivatives of the Diffie cube, right? Because you brought them all over to the other side. And then what you have here is just a whole set of ones. Right? The first lower diagonal is all ones, because all those are is shifts, right? x2 dot is x1, x3 dot is x2, so you're just shifting the numbers in the x dots. So that's a 1. This is called that controller canonical form, but there are many other forms of this thing. This is the one that we're going to put most of our emphasis on, unless otherwise needed. And in fact, in your arrow systems, we're going to need other things. We've got these four-dimensional state space models for the phugoid or for the longitudinal and lateral dynamics, and they are not in a controller canonical form. Remember the ABCDs from 355? The A matrix that you got the eigenvalues from? That A matrix wasn't in that form, because those dynamics are a lot more complicated than a single nth-ordered, fourth-ordered differential equation. There's lots of differential equations. So you get a whole bunch of different elements in the A matrix. It's not in a canonical form. However, if you wanted to, you could put it into a controller canonical form. And this is what the authors talk about here. Let's go to this one, because this one looks like it's the same thing, but it's just a hair different. It's just a hair different because of this term. Remember, the one we just did had a 6 up here, and it had the second degree polynomial down there. Well, so how does this thing differ in its representation than the one we just did? So let's go through this one in detail. Not this modal expansion form, partial fraction expansion form. Forget that. Let's just rewrite this. Okay? So let's look at the picture here and see if this picture that the author gives you actually makes sense. Because now what we have is we have x1 dot, that's y double dot. We have x2, x1 or x2 dot. We have x2, but then we're saying y is 2 this and 1 this. Hello. Before we had, remember what we had, where we had the 6 on the top of the transfer function? It was right here, wasn't it? But now the authors are putting it right here. Huh? Well, it's because there are multiple representations for a state space model. So let's walk through how the authors actually get this form. Here is how the authors get this. Let's write the differential equation out here. The authors say that we're going to define x1 dot. So let's draw the picture. Let's get rid of this picture again. Draw it all over. So We're going to follow the author's equations here. Let's look at this picture and see what we get. X1 dot is right here. And X1 dot, we're going to figure out what X1 dot is here. So we've got U coming in, and we have the integrator here. We have another integrator here. So this is X1, which is X2 dot, and this is X2, right? That's what the authors have there. And let's not worry about this thing right now. Let's just break down the feedback part of this block diagram. So what you have is, now, you know, actually I did it wrong, didn't I? I didn't use the author's notation. I actually used negative signs here and put positives in here. Well, who's right? So we can do the same thing here, can't we? Except I gotta tell you, who prefers that block diagram right here with, and just look at the feedback, right? You got these three feedbacks. Who prefers that notation, or do you prefer this notation? One. Why?
Because it looks simpler.
Yeah, there's too many damn summations in there. It's all one big sum. It's like, how many Rube Goldberg summations can you put in here? Why didn't the authors just feed it back just like they did in the last one? I think they wanted to intimidate you. First of all, they put a sigma in here. Oh, they actually had a sigma in the other one, and I put a sum sign. Because I never really was a fan of Greek. Sigma means summation. So let's draw that block diagram. Right here, what we have is this. We have the minus 7 out of x1. So I'm going to do it this way. And then 12 right? Okay, so what is x1 dot? What is it?
Go away.
Come on, let's get the equation for x1 dot.
Minus 7x1 minus 12x2.
That's the first one, right? Does that verify with the author? Oh, you got it. Okay, and now what's x2 dot? All right, so that's the second one. And then we get y equals x1 plus 2 times x2. Where does that come from? Is that what? Remember, what is y here? In this example right here, oh, sorry. In this example, what is y? Well, the transfer function is y over u, isn't it? That should be obvious. So y is equal to what? Y double dot equals minus 7 y dot minus 12y plus u dot plus 2u. Yes.
Would it make sense to try and get the differential equation directly from the transfer function?
We just did that.
Okay.
Yeah, let's draw the parallel here. If we were to do this thing, we had, this was minus 7, right? This is minus 12. This is y double dot, isn't it? Right? That's y double dot. So this is minus 7, minus 12. There is no x3 in this one. And then we would have plus what? Oh, plus something else. Come on. Diffie Q. What's the Diffie Q? Cross multiply and solve for y double dot. U dot plus 2u. Right? So you suggested that we just go ahead and solve the Diffie Q directly, right? So here's one way of doing it. The natural inclination here would be to just leave this like it is and write this thing out. Write it out. Let's write it out directly. What's x1 dot? Come on. Well, what's here? What's there? If I just wanted to write a state space form for this thing, well, how would I write this? How many inputs are there in this equation? 2. U is an input and U dot is an input. So then these guys are the 2 by 2. This is the more natural state space form. If you start, you brought it up. So let's just go back to the Diffie Q and write the Diffie Q up. So let's write the Diffie Q out and then we get this. Right? I personally like that form because I actually like to see how what you got into this system is remember you went all the way back to 266, which is Diffie Q's, right? Or is it 265? 360. I was close. 1,000,009. So, when you make the input, it goes on the right of the equation. Remember, you solve for the homogeneous equation, the initial conditions. Then you say, now let's consider a forcing function to this thing. Well, the forcing function in this differential equation is a linear combination of u and its derivative. And so, me, as an engineer, I like to see how each of these inputs affects the output. So I'm going to call each one of them an input. If I can measure u, if I can control u as the input, then I control u dot as the input too. So then what would, if all I wanted to output here was y, then what would I get? What's that C matrix? Yeah. Right? Because x2 is y. Remember, x1 is y dot. This x1 dot is y double dot. So x1 is y dot. So x2 is y. Right? So we still have this kind of controller form for the A matrix, but we have a different B and C here. And this isn't wrong. It's just, as you said, directly going from the Diffie-Q directly to a state space form without looking at it in this framework. But this framework is equally valid. This is an equally valid framework to say, well, then I can get y from, let's go to the y equation. Y is x1 plus x2, 2x2. Why is that? Hello? Where does that equation, cryptic equation, y equals x1 plus 2x2? Oh, come on. No. I thought it was the 1 o'clock bell. Where does that come from? We can't. Yes, the sound comes from the camera. Where does that red equation come from? 0? Yeah, but can you explain it to me?
x1 equals u dot and x2 equals u.
Where does this come from? x1. Anybody? What? Repeat that.
x1 equals u dot and x2 equals u.
x1 equals u dot. I thought x1 was the integral of x1 dot. Yes.
Does it come from the top of the original transfer function?
It does.
Because then you have the s, which makes, it's really x2 dot plus 2x2.
But you see, this top of the original transfer function is what this equation relates to. Or we're looking at, I assume you were referring to this left diagram?
The transfer function.
Okay, the transfer function, yes. What about it?
top of it is S plus,
I got that.
and then so BS over AS is big Y over big X,
Yeah.
and then you throw big X on the other side.
Write it up. Tell me what to write.
Is this correct? Or is this
Tell me what to write. Come on.
Y, big Y of S over big X of S.
Go ahead.
Equals that, so you don't have
Equals what?
S plus 2 over S squared plus 7
No.
S plus. Okay.
Careful. Careful. Be really careful here. You almost had it.
Should be
Let's
U of S.
let's ignore the numerator. Let's ignore the numerator. All right? If we ignore the numerator, then what we have here is, I'll write out the equation. Correct? This is just for the state. I'm ignoring the numerator. All I'm saying is there's a 1 over that thing. We'll get to that thing later. But let's write this one first. So what's the transfer function matrix between U and X? Let's take the transfer function of this. What happens to this thing when you take the Laplace under zero initial conditions? All right. Is that correct? So this gives us what U is the input now. There's no U dot. U is the input here to this thing, isn't it? You were so close. But you'll see what happens next. So let's draw the block diagram for this. And I'm going to put everything in the S domain to emphasize that we can just multiply. This also, by the way, is U of T. And what's coming out of here is X of S. The state. What's the transfer function between these two? Solve this equation for X of S. What is it? Gather up all the X terms, which means bring this to the other side. Then you have SI minus A, correct? SI minus A times X equals B, this. And so this is the transfer function matrix between the two. You multiply U of S by this, you get X of S. Right? But now I have a transfer function in these between X of S and Y of S. This was the denominator, wasn't it? Remember we said just let's deal with the denominator now. Right? So what we basically did is we took this transfer function and wrote it this way. Correct? But I wrote this in a state space form so that what comes out of here is all three states, not just one state. Right? This is this. Remember, we already did this for state space form. Okay? So this is all done. And now what we have is we have a transfer function here, which is just s plus 2. Uh-huh. So what is y of s? What is y of s? Isn't it? You just multiply? I've got to put a c here now in this form. Well, let's see. This is going to be I got to put that into a state form because I can't. Yeah. In the state space, this thing doesn't make any sense directly, does it? It does, except that if you do this, you get sx of s plus 2x of s. Don't you? But that is not y of s. So what you have to do here is you have to, I didn't want to go to there. Let's just do this. I really didn't want to go there. Nope, I took the wrong path. Wrong path because I got to explain too much of what's going on here. So let's just say wrong path. Because in order to argue that, I have to actually form a matrix there. And I don't want to do that. Because I'm trying to minimize the math for you, and I just dug a hole that's going to require you to make the math for you. And I don't want to do that. So we'll just, because I need to get to the rest of this thing so it relates to your homework, let's just assume that this is correct. It's a state space form. We already had a state space form, didn't we? This is another state space form, and what you find here is this. That what you have in this ABC, this is, oh, I'm sorry, this one now. This is the one we're at. What you find here is that B is 1, 0. That's what we got, right? Over there. B was 1, 0 before I erased it. And C is 1, 2. That C, 1, 2 comes from the block diagram. Right? You just add it in to get Y. So this is the ABCD form. All right? And it's a controller canonical form because that A matrix has the negative of the coefficients of the differential equation, the characteristic polynomial, up here, and then it has ones on the lower off diagonal. So it is a controller canonical form, but it's not the only controller canonical form. It's one controller canonical form, and it's really nice because what you see here is that you have the numerator terms 1, 2 in the C matrix. It's a very nice form, and the authors say that two significant facts about this form are that the coefficients 1 and 2 of the numerator polynomial in B of S appear in the C matrix. So if I give you a really ugly fourth order, polynomial with zeros and poles on it, you can just take the B's and put them in the C matrix, and you can take the A's and put them on the first column of the denominator coefficients and put them on the A matrix, and you're done. right? So if I had this, for example, 3s plus 1 over s squared plus s plus 2. The A matrix would be what? What would the A matrix? Remember, it's these coefficients, negative of those coefficients. So the A matrix would be the negative of this one, and the negative of this one, 1, 0. The C matrix would be what? 3, 1. Now, the reason I didn't want to spend this much time in going through it is because I am not a fan of this state space form. The authors are a fan of it because it's very convenient. Here's the problem. Here's the problem. How much time we got? Oh, it's going to be a quick one. Got to be a quick one. If I have this, let's forget about D right now, okay? How do I compute the total solution to this differential equation? The total solution with initial condition x naught. How do I compute it? This is directly out in this current homework, and you had it in a prior homework. Laplace transform. Let's Laplace transform x dot, and what do you get? Right? Correct? And now you can solve this, the total solution. X of s is this. Isn't it? That's just algebra. Now, let's look at the initial condition response of the system. How do I get the initial condition response solution for the system now? You turn off all the inputs. It's only an initial condition. So for the initial condition response, this is gone. Here's your initial condition response. Right? Correct? Is B in it? Is C in it? No. This is the initial condition response of the system. Period. And if y happens to be the second variable, then I would say C is equal to 0, 1 times x, wouldn't I? Right? If I only wanted the initial condition. But this thing, once you put it in that form and you start computing initial conditions for this C matrix, or the C matrix, because here B is 1, 0, 0, 0, 0, isn't it? All right? So when you take this thing and you put it in here, really nothing happens, because it's all 1. It's just a 1, 0, 0. But the problem is, this gets back into exam 1. In exam 1, problem 1, the very first problem, used all these different state space to transfer function, and they all gave you different B's and C's. And the problem with this form is that if you want to get an initial condition response, you're going to have the same errors with this form that you had with in exam 1. And so that's where we'll pick up next time. So look at the homework for Friday, especially that one with the initial condition response. And if you haven't taken your homework, take it. You want to take a cookie, take it. Take it. I cannot